In this class, we're going to take a look at a type of power series called a Maclaurin series. So if you've been watching the videos in this collection, you've already heard mention of these types of power series called a Maclaurin series and a Taylor series. And I introduced those a few classes ago just to kind of give a sense of the direction that we were going with these videos. So under the broad heading of power series, we've got these two forms, Taylor series and Maclaurin series, that we want to explore a little further, and we're going to start by looking at the Maclaurin series. So a Taylor series and a Maclaurin series are very similar. They basically rely upon derivatives to generate the power series. So let's think about, first of all, what is a Maclaurin series, what does it look like, and then we're going to work a couple of examples to see how to generate the Maclaurin series for a couple of functions. So the first thing is to remember, or maybe just to know for the first time, that a Maclaurin series is centered at 0, whereas a Taylor series is centered at some value other than 0. So let's say that we've got our some function f of x, and we're going to represent this function, or let's say this function can be represented by a Maclaurin series. The requirement, or one requirement, is that that function has to be infinitely differentiable. You have to be able to differentiate that as many times as you want. First time, second time, third derivative, fourth derivative, 100th derivative. That's one of the requirements, because we need that to generate the terms in the series. So what does it look like? Well, we've got our function which is represented by the sum n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial, then x to the power of n. Okay, so notice that that is very similar to the sort of form of just a general power series. In a general power series, let's say you've got some function f of x, and you're setting that up as the power series n equals 0 to infinity of some a sub n x to the n. This would be a power series centered at 0 as well, like this Maclaurin series. So comparing these two, what have we got? Well, we've just really got our a sub n, which, remember, is just the coefficient numbers that go in front of all the different powers of the x terms. That a sub n is really being generated by this sort of function here, this formula here. This formula, though, for a Maclaurin series, importantly, consists of subsequent derivatives. Okay, so if we start to expand out some of these terms, then the first term would be where n is 0. So we're taking the 0th derivative. So the 0th, that sounds really strange, the 0th derivative is just when you basically have got the original function, f of x, because if you think about it, when n is 1, that's going to be the first derivative, so the 0th must just be the original function. So when you've got n equals 0, this becomes just a 1. 0 factorial is also just 1. So the very first term just basically becomes f of 0. So that's always going to be the case. You get this constant term in front. Then we're just going to start powering things up. So we're going to take the first derivative, so f prime or f dash, evaluated as 0. So remember, always with a Maclaurin series, you're evaluating at 0, unlike a Taylor series where you're evaluating at some other value. This is going to be over 1 factorial, which is just 1. I might just write in the 1 factorial there. Technically, this one is, I guess, over 0 factorial, but we'll just leave it like that. Then we're just going to take our x to the power of 1, which will just be basically x. If you like, you can put a 1 on there. Sometimes it's useful to put on all these numbers like a 1s, even though you know that these can kind of disappear, just to see the pattern. And it's really important, if you're working with Maclaurin series, that you understand how these terms are generated. So just moving on then to the second derivative, so f prime prime of, again, 0 over 2 factorial, and then that's going to go with the x squared term. So you can see the correlations already between the numbers, and we'll just maybe do, well, one more. So we get f triple prime, I guess. So the third derivative evaluated at 0 over 3 factorial, and this is going to be then going with the x cubed term. You would just carry on like that. So the nth term would look like this, and that's basically how we generate the series. And this series represents this function, but not necessarily everywhere. Now in this class, we're just having a bit of an introduction to Maclaurin series, but I'll just put out there now, and I did mention it in a previous class, that this here only converges to this function, i.e. these two are only the same thing, sometimes for a limited set of values of x. And that set of values of x, that's called the interval of convergence. Sometimes that's every number, all real numbers, all x. Sometimes it's a far narrower window or far narrower interval of values, but it's really important to identify that. We're not going to worry about that so much in this class. Later on in this collection of videos, we're going to look at how you find that very important interval of convergence. Okay, so if you're working with Maclaurin series, it's really important to learn this general form and to kind of, I guess, almost practice this a little, just to know what it looks like. As you start to churn out the terms, it can get a little messy, so it's really important to keep on top of how these terms get generated. So what I want to do now is to look at a couple of examples. So I'm just going to make some space here. So let's just go like this. We'll just leave this up here as our general form to look at. So the first function I want to look at is f of x equals e to the x. So I would recommend that as you start to build the Maclaurin series expansion, that you do so in a very systematic manner. And what I mean by that is we know that each of these, so we're going to need all of these things, okay? In particular, these subsequent derivatives evaluated at 0. So to generate those, we might want to start by generating them, almost like in a table of values, and then we can just write them into the series at the end. So this here is effectively this is our original function. This is going to be the one that generates this term here. So that would imply then that f evaluated at 0 to give us that term, that's just e to the power of 0. Anything to the power of 0 though is just 1. So that leading term for this particular function, this Maclaurin series, is 1, just a constant term. If we differentiate now to get our first derivative, f prime of x, that is just e to the x again. So this particular function, e to the x, is quite interesting because all of its derivatives are just e to the x. So remember when you're differentiating an exponential function, and they're not always going to be quite this easy. You could have some other number in here beside the x, but the rule is, well, it's basically the chain rule, isn't it? We're differentiating the power, and then we're parking that number in front. So the power here is 1x. If we differentiate 1x, we get 1. So really there's a 1 in here by the chain rule. Because that's only a 1, it just ends up being e to the x. And then we're just going to get all derivatives to be e to the x. Now that's just a kind of quirk of this particular function. If we now evaluate that derivative, e to the x, at 0, again, we're just going to get 1. So let's just churn out a few terms. We'll maybe do the first 3 or 4. In this case, we can just basically write them down because they're not going to change. We know that the nth derivative of e to the x is also just going to be e to the x. So this is a special case in a way because it's very, very straightforward to generate these values. For other functions, you're going to have to work harder to generate these values, as we'll see in a moment. Okay, so it's like that. So what are we going to do with this? Well, basically, we're just going to now take these values and plug them into our series. Let me just put that up here. So that tells us that for f of x equal to e to the x, we can generate our Maclaurin series by going f of 0, which is 1, and add into that f dash 0, which is 1. So all of these are just going to be 1. That's 1 as well. 1 factorial is 1. So we get 1 x to the 1, or just x basically. This guy here is going to be 1 over 2 factorial. 2 factorial is 2, but I might just leave that as a factorial. That's going to be a 1, so I'm just going to pull the x squared on top to make it an x squared over 2 factorial. This guy is going to be an x cubed over 3 factorial, and you can see the pattern now. So you can see that what's actually happening here, and if you consider that this was over, especially if this is a 1 and this is over 1 factorial, this is a 0 over 0 factorial, then this is just equal to the sum n equals 0 to infinity of x to the power of, so remember here n is 0, 1, 2, and 3, so it's x to the power of n divided by n factorial. So in other words, the Maclaurin series expansion for e to the x is this here, but can be given in sigma notation like this. So it's a particularly neat result for e to the x. Comes out to be this very clean looking function. And you'll see that a lot. It's a really common function to work with for Maclaurin series expansions. You can upgrade it to work with different exponential functions by just changing the variable in here, and then you could work through that, and sometimes that will generate some slightly different patterns, but it's always going to be fairly similar to this expansion here. And we'll see later on in different techniques in this series in Calculus 2 that sometimes we do want to pull in these known results, like e to the x or sine x or cos x, things that we already maybe know, and then use them to compare them to a different function which is closely related because it's got a similar Maclaurin series, and by that comparison we can then draw certain results. And you'll see what I mean by that later on. But anyway, for the time being, we're just trying to get this technique down. Let's look at a second example. Let's take a trig function. Let's go for sine x. And let's start to generate our Maclaurin series expansion for sine x. So again, we're just starting by doing f of 0, and then we're going to take subsequent derivatives. You've got to be careful with these because it's very easy when you've got zeros to think the answers are always going to be 0, or in this case it was 1. But here with our trig functions, we need to think a little bit about the sine values, and this is going to turn into cosine when we start differentiating. So the sine of 0, which is what we're evaluating here, is just 0. So hopefully you can visualize that on the sine graph, or you just know that from trigonometry. If we start differentiating, then f prime of x is going to give us the derivative of sine, which is positive cosine x. So then we're going to get f prime evaluated as 0. That's a cosine of 0, but the cosine of 0 is 1, so we get a 1 in there. Taking the next one, f prime prime of x, that's the derivative of cosine x, which is minus sine x. So that then implies that the second derivative evaluated as 0, sine of 0 is 0, minus 0 is 0, so that goes back to 0. So we're starting to generate a little pattern here, which is really a well-known feature of sine and cosine. If we then take the third derivative of sine is positive cosine, so minus sine, the derivative there would be negative cosine x. So that implies then that the third derivative evaluated at 0, that's minus the cosine of 0. Cosine of 0 is 1, minus 1 is what? Minus 1. So it's going to be like that. Notice that if you were to then differentiate again, we're going to stop at that point. If you did, you would have minus the derivative of cosine x. The derivative of cosine x is minus sine x, so you're going to have minus sine x, in other words, taking you back to there. So you cycle through, you get back to here on the fourth derivative, and then you cycle through again. So it goes through that kind of cyclical pattern, which is what you'd expect from a trig function, sine and cosine, because if you even just think about the graphs, they've got that kind of cyclical nature to them. Okay, so we'll stop there at that point. Now we're just going to take these and sort of plug them into our formula. So we're going to get f of x, which equals sine x. And I would really encourage you to try and learn these kind of off the top of your head. If you're working Maclaurin series, it's good to know e to the x, sine x, cos x, and maybe some others as well. So let's just start churning out these values. So the first term is 0, because we've got a 0 here, so we can effectively just leave that one off. So we're going here to this term, we've got a 1 over 1 factorial, which is 1. So it's just going to be 1x to the 1, so that's just basically an x. Then we've picked up a 0 again, so again that's just going to drop out. We're going to keep getting these repeated zeros. The next one, the third derivative, so we're over here now, is minus 1 over 3 factorial. So it's going to be minus x cubed over 3 factorial. And then this would alternate, this would go back to a plus, and then it gets generated from there. So see if you can sort of pick up a pattern in these sort of terms and try and figure out what's going to happen there. I'm just going to leave that, but it's good for you to know the result for this based on this guy here, based like that guy there. It's good to know both the expansion and how to write it in the sigma notation. So yeah, I think we'll just leave that one there. But what I would encourage you to do is maybe churn out a few more terms of this one and see what the pattern goes like. You can see already it's basically missing out all the even terms, and I'll give you a little clue about that. So this is effectively, a 1 here. But remember that for this term here, this is when n was 0, this is when n was 1, this is when n was 2, and this is when n was 3. So the term that we've got here has been generated from when n was 1, so that's represented there. This term here was generated from when n was 3, so you can see that that's represented here and here. So that gives you a kind of clue as to how you're going to go about forming the algebraic form of this series, Maclaurin series expansion for sine x. Try as well cosine x. Cosine x is going to be very similar. You're going to have these alternating sine and cosine functions, and you're going to get similar results because sine and cosine give you the same values for different places. So see what you get with that one. Compare the sine to the cosine and compare it also to the e to the x. They've got a strong correlation. Notice that we're just picking up odd values here. You'll see that for cosine you're picking up even values. So that's just really a bit of an introduction and overview of what a Maclaurin series is. The first thing you need to learn is the general form, both in this kind of compact algebraic form and the expansion. And practice is really important with these. Try and learn to do it almost in this kind of table form before you start chucking the numbers into the expansion. I find that if you try and sort of do this work on the fly as you're generating the terms, it just gets a little messy and you can lose track. So you're better just to generate them on their own first and then just put them into the series and then try and spot the pattern. Is there a pattern here? Can you connect these to the n numbers to therefore generate some general term? And you'll find that in a lot of cases it's fairly obvious because these things tend to generate quite neat patterns, but that's not always the case. So that's our introduction to Maclaurin series. Maybe just practice a few of those. We're going to take this further throughout the rest of these videos, and we're going to start to look in detail at things like how do we sum a Maclaurin series, how do we use Maclaurin series in different ways, how do we find the interval of convergence and the thing called the radius of convergence. So we've still got all of that to explore in the rest of these videos.